All right, today we're jumping into one of the biggest mysteries in modern physics. We're talking about a material called Magic-Angle Graphene. And trust me, it's a full-blown quantum whodunit. A detective story playing out at the atomic level, and scientists, well, they've just uncovered some absolutely incredible new clues.
So what is this stuff really, and why is it so mind-bending? At its heart, Magic-Angle Graphene is a superconductor, but it's not just any superconductor. See, the way it works, the actual mechanism, has been this huge point of debate, pitting two major scientific theories against each other in a real clash of titans.
And the entire story, believe it or not, starts with this one little number, 1.1 degrees. That's it. That's the magic angle. You take two sheets of carbon that are only an atom thick, that's graphene. You stack them up, and you give them this tiny, ridiculously precise twist. And when you do that, boom, something extraordinary happens. All of its electronic properties just change in a flash.
Now, the process for making it, what they call the cut and stack method, it almost sounds deceptively simple, right? You peel off a sheet, you cut it, you stack it. But it's that final step, that tiny, precise twist. That's the whole secret sauce. That's what creates a material where electrons can flow with absolutely zero resistance. It becomes a superconductor. Now, making superconductors isn't new, but why this one works, that's the real puzzle.
And this one question, has created a massive divide in the physics world for years. It's a true scientific whodunit. How in the world do electrons, which naturally hate each other and push each other away, suddenly decide to pair up and flow together in perfect harmony?
So the investigation basically turned up two main suspects, two completely different theories for why these electrons form what are called Cooper pairs and create this amazing superconducting state.
Okay, so here are our two prime suspects. In one corner, you have the conventional theory. Here, electrons get pushed together by vibrations in the material itself. These are called phonons. The analogy on the slide is perfect. Think of the beat of the music in a club pushing dancers together. This is the standard textbook stuff. But in the other corner, you have the unconventional theory. Here, the electrons pair up because of how they're directly interacting with each other. They're ignoring the music entirely. And this is a huge deal, because if it's unconventional, it could give us a whole new recipe for making superconductors, maybe even ones that could work at room temperature one day.
So to crack the case, one team of researchers designed an absolutely brilliant experiment. The whole plan was to isolate one of the suspects, those direct electron interactions, and just see what happened to the superconductivity.
The idea was basically to mute the chatter between electrons to see just how important that conversation really is. To pull this off, they brought another metallic layer incredibly close to the magic-angle graphene. This layer acts like a shield or a screen, blocking the electric fields and basically stopping the electrons in the graphene from seeing each other so clearly.
You know, the setup for this is just so clever. They stacked two separate twisted graphene systems right on top of each other. A big twist between the layers kept them electronically separate, but because they were less than a nanometer apart, that top layer could act as a tunable screen. By adding charge to it, they could effectively turn a dial on the electron interactions in the bottom layer, the one that was superconducting.
And this right here, this is the moment the case blew wide open. See, if the conventional theory was right, then screening that natural repulsion between electrons should have made it easier for the material's vibrations to pair them up. Superconductivity should have gotten stronger. But what happened was the exact opposite. As they turned up the screening, the superconductivity just withered away and died.
I mean, the evidence was just damning. The very electron-electron interactions they were actively suppressing were apparently the main thing driving the superconductivity all along. This was a massive win for the unconventional camp. It really seemed like the mystery was finally solved.
But you know how these stories go. Just as the detectives were packing up their gear, another lab, looking at a slightly different version of this material, uncovered a plot twist that nobody saw coming.
It turned out that unconventional superconductivity was only half the story. The material wasn't just a superconductor. It was a quantum battlefield.
So the second team, they were studying a three-layer version of the material. And in this particular system, they found that the superconducting state wasn't alone. Oh no. It was in this constant tug-of-war with another powerful quantum state that was hiding in the background.
That's right, magnetism. The natural state of this material, it seems, is this incredibly delicate balance, this fierce competition between a phase that wants to be a perfect conductor and another one that wants to be magnetic.
So how on earth do you find a hidden magnetic order that's being totally overshadowed by a powerful superconductor? You have to get really, really clever. You have to listen for its tiny, subtle effects on the system. It's like trying to hear a whisper in the middle of a rock concert. Their technique was to measure what's called the switching current. That's the exact point the superconductivity breaks and resistance suddenly pops back up. But they didn't just measure it once. They measured it thousands upon thousands of times. See, a single measurement gives you one number, but measuring it over and over again reveals a statistical pattern, a shape in the randomness that contains all these hidden clues.
And what they found? Well, it was just plain weird. As they raised the temperature from almost absolute zero, the superconductivity didn't get weaker like you'd expect. It actually got stronger up to a certain point before it started to weaken again. I mean, this is totally bizarre. The only way this makes any sense is if that initial bit of heat was actually helping the superconductor by knocking out its magnetic competitor.
And the second clue? Even more direct. When they applied a magnetic field, the system acted differently depending on the field's direction. This kind of direction-dependent response is a classic fingerprint, a dead giveaway, that there's some kind of underlying magnetic order that's influencing the superconductor.
And finally, the smoking gun. By just nudging the material outside its superconducting state, they found direct evidence of magnetism. The material showed something called hysteresis, which is basically a magnetic memory. Even after they turned the external magnetic field off, the material stayed magnetized for a little while. This confirmed it. The rival magnetic order wasn't just a theory, it was real, and it was living right next door to the superconductor.
So where does all of this leave us? What does it really mean when you solve one huge mystery, only to uncover an even deeper one right underneath?
So let's just quickly recap the key takeaways from this whole quantum detective story. First, we confirmed our main suspect. The superconductivity is definitely unconventional, and it's driven by how the electrons talk to each other. But we also found a co-conspirator, a competing magnetic order. And these two states, they are locked in a quantum battle for dominance inside this amazing material.
And that really leaves us here, right on the edge of a new frontier. We thought we were just trying to understand one weird material, but what we actually found is this incredibly rich playground of competing quantum states. So the next grand challenge isn't just to understand this competition, but to control it, to be the puppet master. And if we can figure out how to do that, we might just unlock a whole new generation of quantum devices that we can't even begin to imagine yet.